Good afternoon, and thank you for joining this afternoon's webinar focusing on the Ansys Explicit STR product within Ansys for looking at dynamic problems. My name is Brian Miller, and I'm delighted to be joined by my colleague Shaquille, who's a principal engineer in our structural mechanics team. For any of you who is not aware of wired analysis, very briefly, we've been involved in providing a full range of analysis solutions for 35 years. This includes multi-physics simulation, FEA, CFD and electromagnetics, safety and reliability analysis, and also focusing on how we can help companies improve the design, including various optimization methods. Over this period of time, we provided a range of solutions to over 1,500 clients, comprising of software, training and consulting. Within our team, we have around 55 staff and associates, and all our project work is accordance to various quality and environmental standards. Within our portfolio, we are a value-added reseller for 7 leading products. Ansys, which obviously is the theme of today, Flownex, which is a 1D fluid simulation package, Plaxis for the detailed analysis of soil problems using FEA methods, Deformer Moldflow, which both focus on solving manufacturing problems in the areas of metal forming and injection molding plastics. And then we have Optimus and Reliasoft, which focus on improving the reliability and optimization of various products and processes. So today we wish to cover in the next 25 minutes or so an outline of explicit dynamics. Why do we want to look at explicit dynamics type problems, and why do we use specific explicit dynamics focused software products? Much of this is to do with looking at the fundamentals of shockwave propagation, which we will discuss briefly. We'll then provide you with an overview of Ansys Explicit STR, mainly through a drop test demonstration showing the workflow and hopefully some results. And finally, after a wrap up, we will be happy to take any questions. And in fact, if you have any questions during the webinar, then you should see a questions panel within the GoToMeeting control. If you'd just like to type in any queries, then hopefully we'll have time to address them at the end. So I'd like now to pass over to Shaquille.
Thank you, Brian. So the first thing we're going to look at is we're going to distinguish between the two types of finite element analysis approaches, looking at comparing implicit and explicit type of analyses. So in this case, implicit and explicit refers to the two types of time integration methods used to perform a dynamic simulation. So if we start off by looking at implicit time integration, so for a transient dynamic analysis, we're solving the equation there that's shown at the top of the screen there, where for an applied force, we can calculate the displacements based on the stiffness of the structure, and that stiffness can be non-linear, taking into account damping and inertial loads. Once we've got the displacements, we can then calculate the internal forces, and those internal forces can be compared to the external forces to see if we've got convergence in our solution. Once we have convergence, we can then go on to the next time increment. In terms of explicit time integration, here we're using a different approach where we're applying principles of conservation of mass, momentum and energy. So we're looking at where we apply our load, we're looking at applying these principles to our structures and working out forces within our elements. Once we've got the forces, we can then calculate the accelerations and then integrate the accelerations to calculate velocities and displacements. We can update our mesh and repeat the process and look at the solution as it progresses, as time increases. So just looking at these two equations, we can see that the implicit method has difficulty when problems are highly nonlinear for convergence issues. If we look at the explicit approach, we can see that there's no convergence checking. There's no inverting of stiffness matrices. So the solution is relatively straightforward to calculate. Just looking at some typical applications for explicit, we're going to start off by looking at shockwave propagation. So shockwave propagation is looking at compressive shockwaves acting on our structure, and as the compressive shockwaves transfer through the structure, they're reflected as an expansion wave, and we can capture the interaction of these waves through our system over time. Because of the equations and the method adopted, we can include highly nonlinear analyses in our work. For example, large deformations and strains. The animation that you see on the right is like a squash ball hitting a wall, and you can see the distortion and deflections in the mesh, and these can be easily captured in explicit STR. Moving on to nonlinear material behavior, again we can include plasticity, highly nonlinear materials, and also introduce failure into our material models. With contact, we can look at self-seeking contact, as we don't know how the structure is going to behave after load's been applied. We can include some sophisticated contact in our analyses. Moving on to fragmentation, we can look at the effects of blast and ballistic type of approaches and look at what happens to our structures. And finally, finish off with a very difficult type of analysis in an implicit, which is nonlinear buckling, where we've got large deformations, nonlinear materials, and contact type problems in all in one analysis. The slide here just shows you some typical applications. I'm going to start off by looking at a typical application of explicit STR, which is a drop test type of simulation. This type of work is commonly used in electronics industry, looking at handheld devices, medical devices, even in nuclear flasks, dropping of nuclear flasks. So here you can see typically what we do is drop from a given height and look at the response of the system over time, looking out for failure in attached components, failures in the material, and looking at the energies within the system. Bottom right hand side, you've got an impact type of analysis, and this one shows a ballistic type of example. But in an impact analysis, we're mainly interested in the energy absorbed by various components. So we can track our energy through the system and over time. Top right, we've got another application for explicit STR, which is metal forming. So here we're pressing a sheet, looking at the highly nonlinear behavior of the material, and also including in that we can include spring back by releasing the load and seeing what happens to the resulting part. And then finally, the soda can, we're looking at nonlinear buckling with plasticity and very complex contact conditions where we can't predict what will touch and what will interact with each other after load's been applied. So next, I'm just going to move on and just touch on some of the fundamentals of shockwave propagation. And really, we start off by looking at the equation of speed of sound, c. So looking at the basic equation, this is simply the square root of the elastic modulus of the material divided by the density of that material. Just looking at some of the numbers for some typical materials, the range for speed of sound is from steel, say 5060, all the way down to rubber, which is 1800 meters per second. So that just straight away gives you an idea of the speed at which the load is transferring through our structures. If we now look at delta t, so the timing step size, we can take our length, our part's length, divided by the speed of sound to work out our delta t. So delta t is the time needed for the wave to propagate through the rod of length L. So based on the calculated speed of sound of various materials, you can see that delta t would probably be very small. So in the calculation of delta t, Explicit STR will automatically calculate these values based on the defined mesh. So it's important that we control our mesh when we're developing our finite element models. That value rarely needs to be overridden by the user, but we can use common techniques such as mass scaling to factor densities of some elements to then make the delta t slightly larger in areas that we are interested. For stability reasons, we apply a scaling factor of 0.9 to our delta t. So we end up with delta t critical, which is referred to as the Courant-Frederick-Levy criteria, or CFL for short. So that's the delta t that's used in our simulations. So the time step must be limited so that a stress wave cannot travel further than the smallest element characteristic length in the mesh in a single time step. So as you can imagine, that delta t varies as the mesh distorts. So I'm just going to put some numbers to that equation. So what we have here is a very simple example which shows a rod. It's of length 1 meter. It's built in on the right hand side, and we have a constant load applied to the left hand side, compressing the rod over its time. So it's steel, so we've got this speed of sound of that material, which is 5,050 meters per second. For a given mesh size, that effectively equates to a CFL number of 1.78 e to the minus 5 seconds. So if I just play the video, you can see the compression wave and the reflective refraction wave progressing through the rod over time. So if that simulation was to be run for 1 second, that equates to 56,000 time steps. If the mesh was refined, so we use an element size that's half that value, that effectively means the number of time steps increases by a factor of 2. What that means is simply that explicit methods are only suitable for short duration events. So moving on to overview of Ansys Explicit STR. So we're going to look into Explicit STR within Ansys. So we are using here the workbench environment to drive our Explicit STR. So we stay within a workbench where we can define our materials, create our geometry, develop our finite element model, solve, and look at results within one environment. So we're just going to move on to looking at an example. So this is the workbench environment, and this is what we refer to as the project page. We've got our toolbox on the left-hand side, which includes the different types of analyses. At the top there, we've got our various menus and icons. So if we just select the Explicit Dynamics option, we get our analysis system on our main project schematic. We can then link some geometry to this example. So we're just going to, in this case, we're going to look at basically a case, 2 parts to the case. We've got a base and a cover that's pushed on, press fit onto the case, and we're going to drop that case from a height of 1 meter. We've selected an orientation, trying to drop it on its corner. So rather than dropping it from a height of 1 meter, what we've done here is calculated the potential energy at 1 meter, equated that to the kinetic energy just before impact to work out the initial velocity prior to impact. So that gives us a value of 4.43 meters per second. The idea of the simulation is to ensure that the assembly remains intact and functional after it's been dropped. So firstly, if we look at the materials, we can go into the engineering data window within Workbench. On the left-hand side, you can see various material models available within Explicit STR, which include various strength models, failure models, and also equation of states models. In our case, for simplicity, we're just going to simply use a linear elastic material. I'm going to use ABS polymer to start off with. To the ABS, I'm going to include density as well as linear elastic material properties. Define a density value and then go on to defining an elastic modulus. So once we've defined our material, we can then move on to the mechanical environments within Workbench. So the example we're looking at is simply 3 parts. The case is made up of the 2 parts, and then we've got our floor on which we're going to drop the casing. So within mechanical here, we've got our layout, which is on the left-hand side. We've got our tree structure. As we click on the various branches, we get our detail box where we define our data. Any information, any messages are reported in the bottom window. Above our graphics screen, we've got our various icons and menus to give us access to various parts of the software. The intention of this is to make sure that the assembly remains intact after it's been dropped. So firstly, what we're going to do is just simply assign the material to these 2 parts. So I've already defined the ABS material, and now I'm going to assign that material to these 2 parts. For the floor, we're going to keep that as steel, but one change I will make is change the stiffness behavior to a rigid body. What that means is simply as the energy within the casing, none of that energy will be absorbed by the floor, and the energy will remain within the casing, which is assumed to be a conservative approach. In our connections branch, got various connections by default depending on geometry tolerances. Parts have been glued together, bonded together. We don't need that in our simulation, so that can be removed. The type of contact that we are using here is more of a generic contact, which anything that can will touch anything else depending on the response of the system. So that's referred to as a body interaction, and we're assuming the body interaction is simply frictionless by definition in this case. As I previously mentioned, the mesh side of things is very important. In terms of the mesh sizing, we're going to define a global mesh sizing of 2 millimeters for the casing, but for the rigid floor, we can specify a local mesh setting of 10 millimeters. We can generate our mesh, and now in version 16 of Ansys, meshing can be done in parallel. So parts are done in parallel, all 3 parts are done in parallel, depending on your computer power. And that gives us our mesh. And typically we would run through the checks of the mesh and look at the quality checks, look at the aspect ratios to see where the good elements are and where the small elements are that are driving our delta T values. Moving on to defining the boundary conditions for this problem. So this is a gravitational drop impact. based on a drop height of 1 meter. So we're simply going to be defining an initial velocity on this part that's acting in the positive x direction. So 4.43 meters per second. In addition to that, we are going to be fixing the rigid floor. Then moving on to analysis settings. The one parameter that we have to define is the end time for the solution. So the end time in this particular case is going to be 5 milliseconds. So that's a very short duration impact event. So we can now solve this, and obviously to save time, this has already been pre-solved, so we can look at the response within mechanical. So the first thing we look at is the deformed shape. We're looking at true scaling, and we can look at how the parts deform over the 5 milliseconds time period that we defined. So you can see from the deformed shape that the cover is separated, moved away from the base after it's impacted the floor. So you can see the clips in the corners of the case separating after it's being dropped and it's moving away. We can also look at the energies in the system. So looking at the energy summary, based on the mass and the velocity of the defined velocity, the initial energy is 640 millijoules, and we can see as it impacts the floor, what happens to that energy over time. We've not defined any damping in this system, so the response continues, and that energy, the kinetic energy, is then transferred to internal energy, which in this case simply means the strain energy. We can go further on to looking at stresses. Bearing in mind this is just simply a linear elastic material model, we can look at stresses in our parts. And again, as this is a transient simulation, stresses vary with time. So we can just simply go on to looking at our maximum stress point and look at the results of that particular time point. So for this ABS material, we have a yield strength of 64 MPa, and so we can see which areas of our base exceed that stress value. We can do the same for the cover. Again, picking out the maximum stress point, putting in the strength, the yield strength of the material, and looking at where the high stresses are. So in this example, just to show how we can design against failure, in this case we're going to be stiffening up the clips. And a simple way of doing that would be to just simply, in this case, would be to change it to structural steel. In reality, you would change the design and make the clips stiffer, but still use the same material. So we can go on to the alternative design, looking at steel. So this is exactly the same setup. Difference being in this case is that we're using structural steel for the case rather than the ABS material. One thing we'll notice to start off with when we look at our results is the change in energy based on the amount of mass in the system. So moving up from 640 millijoules to a revised value of 4,830 millijoules. You can see also from the energy plot is that the 5 millisecond end time was excessive for this particular application. Looking at the deformed shape, you can see we've achieved our target of preventing the casing, the assembly from separating, as the two remain together enclosed as it's being dropped. So this is a very simple example showing you how we can change our designs and rerun the simulation to come up with a working design. So just to finish off, I'm going to hand over to Brian.
Okay, thank you, Shaquille. So just as a summary of what we've shown today, firstly, there are implicit and explicit finite element methods. Implicit methods are those that you may already be familiar with, which are often available within CAD systems and with other Ansys products. Explicit methods are also available in Ansys via the Explicit STR product, and it's highly suitable for demanding applications, highly nonlinear transient applications, as you've seen. There's a lot of benefits of the Ansys Explicit STR solution. And one of those is that it automatically takes care of the time step size. However, you always have to be mindful with any simulation on having a good quality mesh, as that can affect that size and ultimately both runtime and your results. Obviously, due to the nature of the explicit method, it is typically used for short duration events, as you've seen, but also it can be used, and certainly we have used it in the past, for those involving highly demanding deformation, such as in metal forming and in large compression of rubbers. And there's some techniques, including mass scaling, to help with that. And finally, through the demonstration, you have seen Ansys Explicit STR is fully embedded within the Ansys Workbench environment, which is obviously a benefit for anybody who wants to do this type of analysis, because it is relatively easy to set up. And also, if you are already an Ansys user, then you're both very familiar with the interface, and also through the licensing system, you're able to use the same geometry editing, Design Explorer, and even the HPC licensing that you may already have for your FEA and CFD simulations using implicit methods. So just going on, just before we take questions, I'd like to just talk about a couple of training courses and other events that we're doing in the near future. Firstly, regarding Ansys Explicit STR, if you're interested in what you've seen today, or indeed are already a user, then just be aware that we do run the training course, and typically for somebody, a beginner, you can learn how to set up the types of simulations that you've seen today within a 2-day course. We would also run other Ansys training courses, of course, in addition to general theory courses on FEA, and you can see all those at the link as it's shown. If you are interested also in some other workshops and events, then there's 3 coming up. Firstly, for any of you who perhaps also involved in fluid systems, we have a product called FlowNext, which is a complementary solution to Ansys CFD. We have got a free workshop next week where you can actually get your hands on the software and understand when you would use a 1D system at a systems level, which is highly complementary to doing detailed 3D analysis, both CFD and FEA analysis within Ansys. For any of you who are looking at reliability issues within your company, we have a theory webinar introducing engineers to reliability principles. That includes things such as FMEAs and live data analysis, and that's again next week. And finally, some of you may be aware that Ansys have introduced a new product this year called Ansys AIM, which is a truly integrated multi-physics product, all using a single interface, which enables you to do quick and very efficient FEA and CFD simulations at a sort of design engineering level. Again, we're running a free workshop to allow engineers to get their hands on this software, and this will be running on the 19th of August. Details are on our website again, and I would encourage you to register and hopefully join us on the day. So we'd like now to go to any questions you have. I'm just looking at some questions you've got here. Okay, firstly, we have a question regarding whether we can include pre-stress with an explicit model. If you can add anything to that, Shaquille?
Yeah, so we can include pre-stress simply in our projects. This can be done within Workbench by simply doing a static structural analysis first. Once we've done our static structural analysis, then we can drop an explicit dynamics analysis onto our solution. And you can see basically the two are then linked together. So basically giving us a pre-stress structure prior to doing say a drop test simulation.
Okay. How long, another question here, how long does it take actually to run an explicit simulation, I guess, compared to using an implicit analysis?
Yeah, so the casing that you saw there was run on one of our running machines. That's for 5 milliseconds. That took approximately 50 minutes to run using 2 cores. So about 50 minutes to run that particular problem.
Okay, obviously I guess it's very mesh and problem dependent like all simulations.
Yes, of course. Yeah.
Okay, we've got another question here. Okay, so we're looking at components considered on an electronic board for drop testing. I guess the question is if you have components on an electronics board, do you consider them to be rigid, or do we need to mesh them as flexible?
So they can be kept as rigid if we're not looking at components failing or absorbing any energy. But the key thing there is to make sure that we capture their mass and the distribution of mass on the board.
Okay. And a final question. We're aware that, or maybe they use it already, I don't know from the question, but there's also an Ansys LS Dyna product. And what are the differences between Ansys LS Dyna and Explicit STR? Well, maybe I can answer that. I mean, essentially both are very good explicit dynamic solutions. Explicit STR uses Ansys proprietary solver. It actually comes out of another product called Ansys AutoDyne, which has a range of multi-physics capabilities in addition to explicit dynamics. Whereas Ansys LS Dyna has teamed up the Ansys product in terms of the pre-processing, meshing and post-processing with the well-known LS Dyna solver. And some of you may have heard of LS Dyna being used in the past for crash analysis and so forth. Now, in our experience, both softwares are very good and they have their place. The one benefit, certainly, of the Ansys Explicit STR product is that it's particularly easy to use because it's been integrated into Ansys Workbench from ground up. And as we mentioned earlier, it also takes advantage of other licenses within Ansys, such as the HPC licensing, whereas LS Dyna had its own HPC licensing model. So I guess if you have any explicit dynamics problems, then we're pleased to talk to you about the differences of each product, which one is most suitable for you, and we can obviously take it from there. So I think this finishes the questions that we've got today. Hopefully the webinar has been of use to you. Of course, if you have any more questions, then please do not hesitate to contact us using the details on the screen. Otherwise, thank you again for attending and hopefully talk to you soon.